Welcome back to Season 1, Episode 14. This one's about a chook pen. This is leading into the area of optimization that we're going to do a lot more on next year. But for now, I'm going to give you a pretty quick rundown of an approach to questions like this, and hopefully you'll be cool with it. Essentially 5 steps. First one, you end up writing an equation for what you want to optimize. In this case, it wants to optimize the area of a chook pen. So, and it's a rectangular chook pen. So our first step would be, well, area is length times width. We want the maximum area. So we've written a formula for area. Second step is express as one variable. These questions always have enough information that you can simplify things to one variable. At the moment, you've got length and width. We don't want both length and width. We want one variable. So what we're going to do with that is we're told that she has 100 meters of wire mesh. That's the key to this one. Now, wire mesh, that's for the outside. It's essentially the perimeter. So if you remember perimeter, it's going to be 2 times length plus 2 times the width. So we're told we've got 100 meters of wire mesh. So what we essentially do with this information is we manipulate it around so that we can get an expression for L or W. So which one should I go for? I'll go for L. I'll take 2W away from both sides. And then I can divide both sides by 2 just to get L. So L is going to be equal to 100 take away 2W all over 2, which I can simplify to 50 rather. 50 take away W. So we've got an expression for L. We can then substitute in L into our formula for area. So area is now going to be 50 take away W times W. It's going to be easier later on if I expand that, so I may as well. It's W times everything that's in there, so it's going to be 50W take away W squared. At this point, I've got an expression for what we want to optimize, area, in one variable, W. Right, so the third step is remembering that optimal points, minimums, maximums, horizontal points of inflection. All of these stationary points are when the first derivative is equal to 0. Optimization relies on that. We have a formula, we want to optimize area. The maximum, the minimum, whatever we want, it's going to be when the first derivative equals 0. So in the third step, we find the first derivative. So in this case, instead of y and x, I've got dA dw becoming 50 take away 2w. The stationary points are going to be when dA dw equals 0, so I'm going to set that to 0. 0 equals 50 take away 2w. Solve it. Add 2w to both sides. I get 2w is 50. Halve it. W is 25. So it's telling me that there is a particular point. It could be a minimum, could be a maximum. We don't know at this stage. But it's when the width is 25. Now, from there, if I have the width, I have an expression there that tells me the length. So this gets into the... Now, first we'll check the nature, right? We'll check the nature. Is this a maximum or minimum? Or a horizontal point of inflection, for that matter. All right, quickest way to do it with one like this is probably to do the second derivative. So I had the first derivative, second derivative, d2a dw squared. Second derivative of that is merely, you lose the constant of 50, you're going to be left with just negative 2. Negative 2, a negative second derivative, means a maximum, which is good because we wanted to maximize the area of the chook pen, not minimize it. Oh, can you see the work down there? Just. Okay, it's there. Oh well. All right, so the only turning point that's going to exist with this formula is a maximum, right? The only stationary point's a maximum. We're happy, we want it to maximize. Now, the fifth part is we actually have to answer the question. We have the width, we don't have the length. So let's get the length. Thankfully, we know that the length is 50 subtract W. We know W is 25, so the length is going to be 50 take away 25, which indeed gives me 25 as well. Remember our units? They're all in meters, so that width was in meters, that length was in meters. And you may also think, well, the question asks for the maximum area. So we need, what is the area? I could have used that formula for area and just put W into it, but now I have length and width anyway, so if area is length times width, it's going to be 25 times 25. It's actually a square, 625 metres squared. So therefore, maximum area of 625 metres squared when length and width are 25 metres. And that's it for that question. By the way, that happens all the time. Whenever you optimise a full rectangle for area, you end up with a square. You'll see this pattern turn up again.